All right, so for notes today, we need to go through section 1 of chapter 13 in your book. It's on compounds in aqueous solutions. Your objectives for this section are to write equations for the dissolution of soluble ionic compounds in water, predict whether a precipitate will form when solutions are combined, write net ionic equations for precipitation reactions, compare dissociation of ionic compounds with ionization of molecular compounds, identify and draw the hydronium ion and explain why it is used to represent hydrogen ion in solution, and then finally to distinguish between strong and weak electrolytes. It's a lot of stuff to get through, but we'll get it. Okay, so first we need to know what dissociation is. And that's a separation of ions that occurs when ionic compounds dissolve. And you're going to have to understand that there is a difference between dissociation and dissolution. In dissociation, you have ions that separate. So you're going to have either an ionic compound, or we'll talk about later here, an extremely polar compound that can separate into ions. So an example of dissociation, if I put salt in water, that salt is not just going to dissolve, but it's also going to separate into its ions, right? Because salt has sodium and chloride ions in it that can separate in that solution. Dissolution, on the other hand, was just dissolving, right? If you put sugar in water, it's still going to be sugar. It doesn't break up into pieces. It's just those sugar molecules, ultimately, they are very, very small, obviously, too. So your crystals of sugar are going to break up because there are more than one molecule in there. But you're not going to separate in ions. You're not going to see ions floating around. So anytime you see that word dissociation, that's the key. Right, if you're talking dissociation, you better see ions in that solution, separate ions at the end of the day, or else it's really just dissolving. So you already have an example of dissociation here with those sodium and chloride ions when you dissolve salt in water, but it can be any ionic compound. One thing that we want to focus on especially is that if I have a compound like calcium chloride here and it dissociates, you need to recognize that for every calcium, there's going to be 2 chloride ions. And ultimately what we're going to talk about is how for every 1 mole of calcium chloride, there's actually 3 moles of ions that are formed, because separate is different than when they're combined. Right? When you have that compound, if you have that solid, before you dissolve it in water, you just have 1 mole of calcium chloride. Once you dissolve it, all the ions separate, and then you have more stuff to deal with, so you end up actually with 3 total moles of ions from 1 mole of the substance. So counting the moles of stuff is a little different there, but easy enough to catch on to. So you got to look at that specific ratio for those ions. If you need those 2 negatives to balance out that positive, then you're going to have a different number of moles of ions in that solution. Okay, so one kind of reaction we're going to talk about is formation of precipitates. And basically, we've already talked about in this class, you have 2 different compounds that are dissolved in water at the end of the day, and then you mix those things together, and sometimes a precipitate forms, sometimes it doesn't. Basically, what you need to do for any of these kinds of problems is just figure out what new compounds can be formed, and then figure out if those compounds are soluble or not. So looking at this problem here, I have ammonium sulfide that's being combined with that cadmium nitrate. So what I want to look at are the new combinations that are possible, and I've already done that work for you here. You have this combination where you can put the ammonium with the nitrate to make this product here, or you have the other possibility where that cadmium can join up with that sulfide to make this product here. We just have to figure out which one of those products is soluble and which one isn't. Because if there's a precipitate, one of those things is not soluble and it's going to come out of solution. So all you have to do is look at the rules. The rules are in your notes, they're down at the bottom, and there's just those general solubility guidelines. You just go through that and figure out which one of those two compounds, the ammonium nitrate or the cadmium sulfide, is most likely to be the precipitate. Now, right away in guideline 1 and guideline 2, you can see that ammonium compounds are soluble and most nitrates are soluble. So that first product there, more likely than not, is aqueous, right? That is soluble, which already tells you that the other product is probably your precipitate. You still need to go ahead and check with your rules just in case, right? You look down and you see that in that guideline number 6, it says that most sulfides are insoluble except those of calcium, strontium, sodium, potassium, and ammonium. It didn't list cadmium there, so this sulfide is probably not going to be soluble. It should be insoluble. It's not one of those exceptions, so I'm going to put an S for solid here. I might also put that down arrow because that means a precipitate as well, but you have your prediction at the end of the day. You just follow your guidelines. Whatever thing is soluble will pretty much narrow it down for you to figure out what isn't soluble. But I know from the rules that ammonium nitrate almost always soluble, and sulfides are unlikely to be soluble unless you have calcium, strontium, sodium, potassium, ammonium. So I know that's going to be my precipitate. Okay, so then we need to talk about net ionic equations. Those are reactions including only the ions undergoing a chemical change. And we're going to have to be able to identify spectator ions, which happen to be the ions that you're going to find before and after in a reaction. Those things are not going to be included in your net ionic equation. So we need to be able to make those things. So I'm going to write a net ionic equation for the reaction of aqueous solutions of zinc nitrate and ammonium sulfide in this example. So I just need to know what those things are first, or else this doesn't work out very well. So I know zinc has a +2 charge and nitrate's -1. So it should look like this. And then I'm going to combine that, better put my aqueous here, with ammonium sulfide. In this case, I'm going to need 2 ammoniums with a +1 charge to balance out a sulfide with a -2. But I'm going to combine those two things, and I'm going to write a net ionic equation. There should be a reaction, so one of these things is going to form a precipitate at the end of the day. So this is how you're going to do that ultimately. All right, first you need to reform new products, right? So you can kind of ionize everything and then kind of split things up at the end of the day, but I just like to put one thing with the other. So I'm going to do zinc with a sulfide, And I'm doing that down here because I just don't really have room up there. Both of those have a 2 charge, a +2 and a -2, so it should just be 1 to 1. And I gotta check on that to see if it's soluble or not, so I'm not gonna write aqueous next to it. But then I'm also gonna have the nitrate and the ammonium. Remember, the ammonium goes first because it's positive. And again, that's actually a 1 to 1, +1, -1. But I should recognize that I have 2 of each of those things here. So I'm probably going to end up with a 2 out in front there. But now I got to decide what's soluble and what's not soluble. Again, if I go back to my rules, this is almost the same as the one before. Ammonium and nitrate, right, according to guidelines 1 and 2, are almost always soluble. So I can go ahead and put an aqueous behind this because I'm pretty sure that's the way it's going to be. But then again, guideline 6, most sulfides are insoluble, and this is not calcium, strontium, sodium, potassium, or ammonium. It's zinc instead. So I know that that is going to be my precipitate. That is what was reacting, right? That's the only thing that went through a change. The zinc and the sulfide, they were originally aqueous, now they're solid, they're precipitate. So that's all you're going to need in your net ionic equation. So my next step is to just go ahead and get rid of spectator ions. Things that are aqueous on both sides, like the ammonium and nitrate, don't really even need to be there. You just need this equation at the end of the day. I should have a zinc with a +2 charge that's aqueous, that's going to combine with a sulfide with a -2 charge to form my zinc sulfide product. That's a solid, right? That's my precipitate. So that is my net ionic equation. Is what I'm looking for at the end of the day. I might also be asked to identify spectators, and in this case, my spectators are my nitrate and my ammonium, because I had those ions floating around, but at the end of the day, they didn't actually change. They stayed aqueous, so they're just spectators. They didn't go through a change. I don't need to put them in my net ionic equation, but I might still be asked to identify them. So you're going to do lots of examples of that on a worksheet, just to kind of get used to the idea. You can ionize those things before to see the different ions, but if you can flip-flop and you can balance things appropriately, it should be okay at the end of the day. Now, if my precipitate was supposed to be the ammonium nitrate, I have to make sure that it's balanced, and I have to know that I had 2 of the nitrate ions and 2 of the ammonium ions that are combined to make 2 ammonium nitrates. So I might have to account for that in my net ionic equation, but in this case I just had 1 and 1 to make 1, so it is what it is. Alright, so we're also going to talk about ionization, because you can also form ions in different ways. It doesn't have to start out as an ionic compound that dissolves in water. It could also be an extremely polar compound that becomes ions as a result of the action of that solvent, because that water is really attracted to the parts in that molecule. So this is when you throw something like HCl, which is a compound. It is a molecule. It's not an ionic compound. It's a covalent compound, but it's a really polar one. There's a strong pull of electrons towards that chlorine atom, and this will ionize when you put it in water. Which is what makes this an acid, because it contributes to this hydrogen ion in solution. Now, the reason why this happens is because the attraction between water and the hydrogen and the chlorine separately is stronger than the attraction between the hydrogen and the chlorine itself. So I'm going to break that bond because those ions ultimately are more attracted to the water than they are to each other. Okay, so I'll try and show that to you in this next thing where we talk about this hydronium ion. Because in reality, we're going to talk about acids, and we're going to talk about how this thing over here, this hydrogen ion, doesn't really exist just all by itself. It's got to be part of something else. So what's really happening when you throw this into water is you start out with a water molecule and your hydrogen chloride, that hydrochloric acid, and there's a really strong attraction here between the two things. That's a hydrogen bond. And ultimately, because of that very strong attraction, stronger even than this bond holding the hydrogen and the chlorine together, you're going to have that bond break, and a new bond's going to form between the oxygen and that hydrogen. You're ultimately going to make this molecule here with 3 hydrogens that actually has a +1 charge overall that's going to be called my hydronium ion. And then I'm going to have a chloride ion that's separate from that. That's the real reaction. That's what actually happens. That hydrogen is taken from the chlorine by a water molecule to form that hydronium ion. At the end of the day, this hydronium ion, you're not usually going to see it drawn out like that. You're going to see it like this. There's 3 oxygens and a hydrogen. Or sorry, got that backwards. 3 hydrogens and an oxygen, and there's a +1 charge. So that's my hydronium ion. But I just wanted to draw that out so you could see it. When it said that those ions were formed by the action of the solvent, they mean literally the water pulled the hydrogen away from that chlorine to form hydronium and to leave that chloride ion behind. Okay, and then the only thing left in the section here is to talk about strong electrolytes and weak electrolytes. I'll show you these things a little bit more when we get going here, when I get back tomorrow. But strong electrolyte is anything that conducts electricity well when dissolved in water, right? We talked about electrolytes before, but a strong electrolyte is one that is completely dissociated when you put it into water. Now, remember, dissociated means you have ions. You needed that for an electrolyte anyway, but it needs to be completely dissociated in order for it to be a strong electrolyte. So if I have an ionic compound, like sodium chloride, that can be a strong electrolyte. It's going to be completely dissociated when I put it in the water. But I can also have a strong acid, like hydrochloric acid that I showed you on that last slide. A strong acid is going to completely dissociate in water and therefore can be a strong electrolyte, whereas weak electrolytes are going to conduct poorly. They're partially dissociated. Some things are not necessarily going to dissolve easily and or will not dissociate completely. So if you have an ionic compound that's not very soluble, like the ones we've been talking about, right, a little bit of any ionic compound is going to dissolve technically, is going to dissociate technically. But when they say that it's insoluble, say you have like calcium carbonate, and according to your rules, that's not supposed to be soluble according to those guidelines. Technically, a little bit will dissolve, and yes, it will conduct electricity, at least partially. But since it's not soluble, versus this sodium chloride up here that's aqueous because it is soluble, there's a difference. But I'm also going to have weak acids that we're going to talk about later that don't dissociate completely, and those also fall under that weak electrolyte. So I'll show you an example later. If I have this acid, it's actually going to be vinegar, right? That's acetic acid. It doesn't dissociate completely, so I'm not going to have a strong electrolyte here. It's not going to conduct electricity very well, although it's still going to conduct electricity. So I know that doesn't really make any sense right now, but I'll show you some examples. We'll talk about it more later. You'll be fine. So go ahead and work on that worksheet that you have to do, trying to do those net ionic equations. Finish up your worksheet for section 1 if you haven't already. We'll probably have some kind of quiz when I come back tomorrow for school, so be ready for that. All right.